그 스탠포드 유니버시티에 지금 현재 시니어 스텝 리서치 사이언티스트로 계시는데 박승민 박사님은 서울대 물리과에서 학사를 하시고 코넬 어플라이드 피직스죠?
네, 맞습니다.
예, 어플라이드 피직스에서 박사를 하시고 유스 버클리 바이오메디컬 엔지니어링에서 포스닥 하시고 그리고 스탠포드의 그 약대 스쿨 오브 메디슨에서 현재 리서치
의대입니다,
사이언스
교수님.
예?
의대입니다.
의대입니까? 약대가
예,
아니라
예.
죄송합니다. 그래서 시니어 리서치 사이언티스트로 계시고 최근에 그 스마트 토일렛으로 카나리아라는 것의 그 회사를 코파운딩을 하셨네요. 예, 그 박 박사님 그 공유 시작해 주시고요.
네네,
그래서 오늘
교수님.
박 박사님께서는 그 엔지니어링 프리시전 헬스라는 제목으로 강연을 해주시겠습니다. 큰 박수로 제가 대표로 박수를.
네. 네, 감사합니다, 교수님. 오늘 발표는 영어로 진행을 하겠습니다.
예.
예. Today, it is my great honor and privilege to share my work on precision health in front of members of my alma mater. My name is Seung-min Park. I recently promoted to the instructor in the Department of Urology at Stanford University School of Medicine. Before I start my talk, I would like to briefly pay tribute to my mentor, Dr. Sanjeev Gambier. I have been fortunate to work with Dr. Gambier for the last 6 years. Sadly, Dr. Gambier recently passed away from cancer on July 18, 2020, the very disease that he wanted to defeat with his lifelong vision of early disease detection and precision health. He was the chair of radiology at Stanford University, was a global leader in advancing techniques for molecular imaging and early cancer detection. He was a visionary scientist who was resolute in finding novel ways to transform the current healthcare system. His vision has driven Stanford to shift its focus from precision medicine to this more effective, proactive approach to human healthcare, precision health. In this talk, first of all, I would like to introduce to the newly emerging concept in the field of medicine, precision health. Then I will introduce two main projects I have worked on this behalf. In the end, I'll briefly discuss my research summary and acknowledgement. In 2015, in the States of the Union address, President Obama announced the launch of Precision Medicine Initiative, a bold new research effort to revolutionize how we improve health and treat disease. This was an historic moment in the emergence of personalized medicine as an integral part of future healthcare. And we look forward to seeing the research outcomes that will emerge from the $215 million investment into patient-powered project. In 2016, Dr. Eric Topol was awarded this grant from National Institute of Health to lead a significant part of Precision Medicine Initiative, a prospective research program enrolling 1 million diverse participants in the United States. Although clinicians are able to tailor therapies to address the disease process of each patient, but there are a considerable disadvantage owing to the possible delayed treatments. So I think equal emphasis should be given to the disease prevention and early detection as well as a disease treatment. So let's turn our attention to the newly emerging concept in the field of medicine, precision health. The rapidly evolving field of precision health has expanded its effort in prevention and early detection of disease via risk-tailored longitudinal monitoring. In contrast to the precision medicine, which is known to be reactive to the course of disease manifestation, precision health is poised to be more proactive and personalized healthcare that empowers people lead their healthier lives. It mainly focuses on the prevention and early detection of disease via longitudinal monitoring of an individual. As in this diagram, my mentor, Dr. Gambier, predicts its implementation in real life. Even before a person is born, prenatal genetic screening can be already performed. Along with family history and socioeconomic factors, risk assessment can be given. Based on this assessment, precision health may provide the person with a customized monitoring tool for their lifelong healthcare. These tools span the implantables, wearables, smart home with the biomarkers, and imaging modalities. All generated data by these monitoring tools will be fed into the integrated health portal, which analyzes health patterns of a person with predictive modeling with digital twins. As part of proactive healthcare, the portal can recall a person for early intervention of disease for a prophylactic purpose. One of the major components to implement precision health is a low-cost, repeatable, and reliable technology known as smart healthcare materials and devices. With smart healthcare materials and device, I envision that the most effective way to monitor a human body is to utilize the emerging smart home system. Devices in the home or automobile are capable of passively monitoring biological fluids, human behavior, and physiological signs. These measurements ranging from the dietary habits to urine and stool analysis. Passive monitoring approaches permit high-frequency monitoring without requiring a change in a user behavior. Although blood is by far the most well characterized, the requirement for needles precludes it from being an ideal candidate for repeated longitudinal monitoring. Thus, an ideal precision health biomarker should be monitored both non-invasively and passively, as devices that require behavioral modification will ultimately limit user adoption. A smart toilet could seamlessly integrate urine and stool analysis as part of routine toileting events. So smart home requires a new type of the biomarkers, digital biomarkers. They are physiological, biochemical, and behavioral data that can be collected by the smart sensor, which are inherently quantitative. These biomarkers can be collectively analyzed with the predictive modeling and artificial intelligence for pattern recognition and enable actionable response determination. One great example of the digital biomarker is a Stanford study to utilize smartwatch data to screen pre-symptomatic COVID-19 patients. They are everywhere in smartwatches, phones, home appliances, however, barely in the bathroom. So it is expected that the ultimate form of digital biomarkers are longitudinal biochemical analysis of biofluids of interest because the biofluids contain a wealth of health-related biomarkers. Nonetheless, this type of biomarker requires heavy sample preparation and signal amplification processes. In this regard, I have accumulated broad knowledge and experience in developing such devices to generate biochemical digital biomarkers. My ultimate goal is to establish a human health model with multiple human health factors. Current healthcare can only provide a snapshot of human health so that we may miss important health events by neglecting time derivative of these biomarkers. Precision health will better elucidate individual phenotypic signature, improving diagnosis, and revealing information about variants in gut, voiding health, and disease. Let me introduce you to the first example of smart healthcare devices that can reliably collect digital biomarkers. The first example is Precision Health Toilet, as known as Smart Toilet. A relevant research work and perspective commentary were recently published, and all studies shown here in this presentation are IRB approved with more than 300 study participants. Just before I started, as I mentioned, Dr. Eric Topol, and Dr. Eric Topol endorsed the smart toilet work in his Twitter last year. As per my personal correspondence, Dr. Topol endorsed our work as a landmark in precision medicine and precision health. The concept of smart toilet has been discussed in the medical engineering community for some time, but with little output. I am very much sure that one of you must conceive the similar idea at some point. I have uniquely addressed this as a smart healthcare device. Here are the criteria for the wide deployment of the precision health toilet. First, it has to be affordable for the widespread use. The #1 toilet company, Kohler, is selling premium line of the smart toilet system at a cost of $10,000, which majorly focus on the human ergonomics instead of healthcare. Instead of changing the whole toilet, I believe a mountable format would be more cost-effective and widely deployable. Second, it has to measure the human excretion. One counter example is from an academic research group from Rochester. In their smart toilet, they measured electrocardiogram from the toilet seat, which is not directly linked to the human excretion. Third, it has to be performed in the background. If it increases the level of human intervention in measurement, it is less likely succeed as a healthcare devices. Fourth, the collected data should be in the format of clinically applicable and actionable. Fifth, the collected data should be transferred to the health portal securely and safely so that we can combine those data into the EHR, electronic health record, or electronic medical record. According to the guideline, in the first prototype, I focus on the clinically relevant assays such as urinalysis, uroflowmetry, defecation monitoring, and biometric identification. I try to minimize the sample preparation step or even no sample preparation that usually requires tremendous scientific and engineering effort. But all of those, the module that I introduced here is a clinically relevant assays. Before starting the development, I surveyed the medical doctors, especially in colorectal and urologic clinic. I directly asked a colorectal surgeon with the following question: what functionality in the smart toilet would benefit your medical practice? And doctor answered, well, my usual first question to a patient is, how's your stool today? He also mentioned that there are issues regarding patient recollection bias from especially those who are elderly or less educated. In this regard, the surgeon utilized a card developed by a Bristol Royal Infirmary in 1997 called Bristol Stool Form Scale. It is a diagnostic medical tool designed to classify human stool into 7 different classes and indicate the stool's liquidity and morphology. This scale has been adopted in the clinic for the diagnosis of the irritable bowel syndrome and used for the therapeutic evaluation of chemotherapy. As listed here, it is composed of everyday language for lay people. However, it is still reported that professional analysis by physicians are much better than those of the result obtained by the patient or nurse. Therefore, I decided to use artificial intelligence to create an objective and professional way to classify stools. In 2014 ImageNet competition, convolutional neural networks were trained on 1.2 million image sets in over 1,000 categories. The winning entry has less than 10% error rate. Already, Google allows any users on the internet to use their architecture, Google Inception v3, which is deprecated nowadays though, and also known as a TensorFlow. One example posted in the public domain is flower classification. Google made an example to classify stools according to their input images. One of the most powerful features of the Google Inception v3 is that it allows a transfer learning. Transfer learning allows us to deal with a new classification task by leveraging the already existing label data of some related task or domain. In practice, I use this system by swapping the last layer of the already trained network with our stool images. However, proper labeling of a training set is necessary for highly accurate classification. Even though I can do the stool classification by myself, I invited 2 board-certified colorectal surgeons who have been trained on such tasks. Since human stool is regarded as part of human subject, I first started accruing images from the public domain. Finally, I acquired 2,360 images from the internet search, including Bing, Yahoo, Google, finally reaching approximately 20,000 images. According to the surgeon's classification, it spans all 7 different stool classes. To gauge CNN's performance, I benchmarked its performance against medical students. 6 medical students were recruited to grade all stool images altogether. They are originally aware of a Bristol stool form scale, but have never been trained on such task. The ground truth of the displayed receiver operating characters curve was provided by the classification by those surgeons. In the training set, of course, the algorithm outperformed the medical students with the least area under curve value of 0.97. In the test set, the algorithm demonstrated comparable performance with medical students with at least the least AUC value of 0.91. After completion of the software part of the stool module, I implemented the actual system in a mountable format to any existing toilet. First, I salvaged an electronic bidet system, then a commercially available mini computer based on Linux called Raspberry Pi is installed with a Pi camera attached. This camera is located in the middle part of the bidet housing and facing downward to the toilet bowl. In order to provide a constant lighting condition, an LED strip is attached alongside with the toilet seat. Also, a pressure sensor is located underneath the toilet seat, and the LED and the pressure sensor are of course regulated by the Raspberry Pi computer. The video is an example of installment we have in our lab. This is an example of a participant seated on the toilet system. As the inset shows the pressure sensor, after the sitting, the ADC output can be read as the plot shows. In this plot, we can estimate the total sitting time as 129 seconds. While the pressure sensor is on, photos of toilet bowl are taken and introduced to the first layer of the CNN to determine the state of the toilet bowl. I simply classify the toilet state into the 4 different classes: clean, urine, stool, and toilet paper states. From these parameters, I was able to obtain the first stool dropping time and actual defecation duration, which are a good indicator of bowel function. If the toilet state belonged to the still states, then the images were introduced to the second layer of the CNN to determine its VSFS. Altogether, I was able to collect the total sitting time, defecation time, first stool dropping time, stool classification, so that the lower graph shows the 10 consecutive defecation events from the same research participants. Here are some more accrued data from 11 participants with 55 defecation events. I also compared the performance between the user and our CNN, indicating our approach has 20% higher accuracy than users. Also, analyzing the pattern of BSFS over a longer period of time would provide a valuable medical feedback to users according to their pattern. So another feature integrated into this system is to extract the color from defecated stool in the toilet. This can be implemented in real time in situ so that the user will have an objective determination of their stool color, which may indicate some complication in their gut health. iPhone and Android applications are available to cover a non-smart toilet environment. This will be beneficial for global health application. The next module I'm introducing is uroflowmetry. Uroflowmetry is a measuring of basic parameters from urination. A uroflowmeter with a spinning disc principle is a major equipment in the Stanford urology clinic. However, installing a spinning disc in the toilet is very challenging. Therefore, I decided to use 2-camera system to utilize a stereo vision with the OpenCV. The 90-degree angled 2-camera system is recording a urination event. Then the urine stream is isolated from the background. Using the triangulation, I can estimate the volume of the urination and the duration of urination. The upper panel shows the schematic of the system configuration and data processing. The lower left panel indicates the correlation between the read from the uroflowmeter in the blue and the read from the computer vision in red. The urine duration was calculated by the computer vision that has a great and excellent correlation with the uroflowmeter with a Pearson R value of 0.96. In addition, the urine volume estimation by the computer vision showed a good correlation with the uroflowmeter with the value of the 0.92. Another module that I integrate into this system is urinalysis module. When you go to the clinic, sometimes the clinic asks you to provide a cup of urine. Most of the cases, they want to perform a urinalysis test on it. Urinalysis usually includes a visual exam, dipstick test, and microscopic exam. I have focused on the dipstick test, which can provide 10 biomarkers activity from a single urination event. This dipstick is cheap and provides a semi-quantitative results of the biomarkers. I just want to note that this module is only designed for a male who wants the sitting position for the urination. A passive infrared sensor is detecting the urination events, and a mechanical arm is delivering a strip into the stream of the urination. After a certain amount of time, the strip is retracted to the housing, and the colorimetric change is recorded by the CCD camera. Acquired data is sent via Wi-Fi or 5G if any anomaly is found in the data pattern. The user will be notified. A toilet may be shared by your roommates or household mates. In these usual scenarios, it is highly important who's generating what, especially when this system will be connected to the healthcare system. Therefore, I devised a fingerprint recognition system in the toilet flush lever. Each time a user triggers a flush lever, the user's identity will be annotated with all generated data by the Precision Health Toilet system. I have tested this scanner 410 times, and it gave me a reasonable recognition accuracy with an AUC value of 0.95. I also invented a biometric identification method utilizing the human anus. Simply using 3 different computer algorithms, I was able to conclude that the human anus can be very distinctive so that it can be used as a biometric identifier. We are the very first research group that finds the human anus can be used as a biometric identifier. Currently, the system is evolved as an IoT device that can connect to your home to the neighboring hospitals. Based on the Amazon Web Service IoT architecture, we are working with a network service provider to enable secure and safe transmission of all generated data from smart home devices. This Precision Health toilet is directly linked to the very private events. The user acceptance level must be gauged, since the privacy is one of the most concerning issues when we started this project. Due to the proprietary issues, the Stanford community was chosen for the survey takers. Overall, the survey participants acknowledged their favorable acceptance toward the smart toilet usage. One interesting parameter is that statistically, smart home owners are more favorable towards smart toilets. My future plan is to further develop the Precision Health Toilet system as follows. First, I will seek an opportunity to deploy the smart toilet unit to a smart city, and in parallel, microbiome and other biochemical detection of infectious reagent or cancers will be targeted and analyzed in the toilet. In addition, continued COVID-19 surges have highlighted the needs for the widespread testing in addition to the vaccination for disease containment. SARS-CoV-2 RNA can be found in the fecal matter, making human stool another potential source for the COVID-19 diagnostics. So I envision that potential strategies to use a smart toilet platform to passively monitor COVID-19 surges, enabling early detection of infected individuals and promoting the public health. Directly linked to our survey, known ethical issues on continuous monitoring need to be discussed, and we are preparing a viewpoint article that will be submitted to the Science Translational Medicine in no time. I have been actively involved in the Project Baseline, which is a broad effort to map human health led by Verily Life Sciences, formerly known as Google Life Sciences. I have served as a data scientist in this project. This project collected phenotypic health data from approximately 10,000 participants over the course of at least 4 years. The assigned budget for a single person is approximately $30,000. My role is to establish a human health model from this big health data, and I plan to continue this research while developing other smart healthcare devices. I will actively look for an integration opportunity for a developed device. So let's turn our attention to a different topic of research. As I previously mentioned, blood is by far the most well characterized. Thus, I will talk about my contribution to establishing a blood-based diagnostic and prognostic system. This research was enabled by the generous funding provided by NCI under NIH. This work was performed in the Cancer Center for Nanotechnology Excellence. I will majorly introduce you the single circulating tumor cell profiling system. In the end, I will introduce to the in vivo circulating tumor cell enrichment system that I have been heavily involved in. A cancer type, I was interested in a lung cancer. If it is not diagnosed early, it is a cancer with a very poor prognosis, and globally, it is also the most common cancer due to smoking in the developing country. About 85% of patients are diagnosed with the lung cancer already developing significantly, and 80% are directly or indirectly affected by smoking. Of all lung cancer, 85% of non-small cell lung cancer, and there are various treatments, but the treatment that has recently been in the spotlight along with the immunotherapy is targeted therapy. It has fewer side effects than conventional chemotherapy, and it is found to have a significant treatment effect in a certain patient group. Next, I will briefly summarize the lung cancer diagnosis process at Stanford Hospital. If the patient has a higher risk factors or comes to the hospital because of the symptoms, computed tomography is taken to check the lung nodule. The doctor will work with the radiologist to see if the nodule has been stable over the last 2 years, and if so, a follow-up routine is recommended. If a lung nodule looks dangerous, the probability of cancer is calculated through the questionnaires or other examination. If the probability of cancer is low, it is recommended to continue to take CT to see if the pulmonary nodule is enlarged or metastasized. If the probability is moderate, PET-CT is taken to determine if it is tumor, or the lung tissue is examined using bronchoscopy or TTNA, transthoracic needle aspiration. If the probability is high, surgical resection is performed. However, all of these regimens are quite invasive, and the importance of in vitro diagnostic is increasing. In vitro diagnostic is expected to be able to increase sensitivity when the probability of cancer is low, and it is expected to increase specificity when the probability of cancer is high. To diagnose and manage lung cancer in vitro, circulating tumor cells in the blood have been used through a process called liquid biopsy. Tissue cells released from the primary tumor are freely floating around in the blood, then settle in other organs to form colonies. This process is called metastasis. In other words, if you understand the circulating tumor cells, it will be easier to understand the metastatic processes. In the United States, one can check if there are circulating tumor cells in your blood with one click on the internet market. It is a method developed by Johnson & Johnson called Cell Search, but it is not covered by the insurance yet. So we can get the blood test about like $900 here. The important fact here is that what you are looking for through this cell search is not a cancer diagnosis, but the cancer prognostication. This graph here is a Kaplan-Meier curve from circulating tumor cell count and cancer prognosis published in New England Journal of Medicine. In breast cancer, if more than 5 circulating tumor cells are detected in 7.5 milliliters of blood, the prognosis is very poor. Immunocytochemistry is the basis of the CTC identification. Cells are fluorescently labeled using a cell surface marker. As you may know, these markers are cytokeratin and DAPI, but these markers are exclusively used for the cancer cell detection. Rather, you can see it as an epithelial cell marker, which is made under the assumption that there are no epithelial cells in the blood. So oftentimes, circulating epithelial cells get caught into this method. If the patient has inflammatory bowel disease, IBD, especially diverticulosis or Crohn's disease, this inflammation causes epithelial cells to float in the blood vessel. It is reported that 37 circulating epithelial cells are detected when the blood of patient is filtered using the same cell search device. And as many as 41 cells may be detected in patient with a myocardial infarction. The 5 cells mentioned earlier are the threshold values for the numbers of CTC for poor prognosis. To solve this problem, I tried molecularly analyze of CTCs using these 2 nano devices shown here. In this brief video, the overall CTC isolation and detection process is described. First, iron oxide nanoparticles were introduced into the patient blood. Cellular markers antibodies are attached to the nanoparticle. This antibody recognizes cancer cell, and all the cells first pass through the device called the magnetic sifter. Iron oxide nanoparticles are easily attracted to the magnetized surface, so it can separate circulating tumor cells. The isolated circulating tumor cells are spread evenly on a device called the nanowell. A PCR reagent can be performed in situ by adding an LT-PCR mix on the top of it, and up to 4 gene markers can be identified with the different fluorescence. As a pilot study, about 2,000 culture cells, cancer cells were sparked into the 2 milliliter of the healthy blood and passed through the process mentioned earlier. Our gene markers are 4 markers selected using meta-analysis after searching 400 articles in PubMed. Telomerase-related genes, MET genes, mesenchymal genes, and ALDH stem cell marker genes. In white blood cell, only vimentin was seen, while cancer cells have all 4 gene markers expressed. When counting the number of CTC expressing TERT gene and MET gene simultaneously through the patient sample, they can be classified with an accuracy of about 95% or more in 55 samples. And the expression of the gene markers of individual CTC can be determined, like as you can be seen here. After careful consideration of how it can be clinically translatable, we decide to employ mutation markers. In this case, we may use a customized targeted therapy through early mutation detection. Here, 3 mutation, exon 19 deletion, 2-point mutation including L585R and T790M that occur most frequently in lung cancer. Mutation assessment is typically performed by tissue biopsy so that we may be replacing or supplementing the current tissue biopsy. We envision that our screening with the mutational profiling will help patients determine their second-line therapies. In order to verify the feasibility of the liquid biopsy, we analyze blood sample from patients having certain mutation in their primary cancer. The first patient was a patient with exon 19 deletion, and only a mutation gene was detected in all detected CTC. The second and third patient were diagnosed with the point mutations, L585R and the T790M respectively. In this case, both wild type and mutant type genes were found to be detected in CTC. Last, to solve the problem of partial blood sampling, which is chronic problem of in vitro diagnostic system, I will show you in vivo CTC detection project. I conceived this idea in 2013 with a medical doctor, Dr. Ophir Vermesh, and finally it was published in 2018. In this case, the goal was to detect and enrich CTCs in vivo using a device such as stent in collaboration with an interventional radiologist. We have shown that with the porcine model, we can detect much larger amounts of CTC with a higher capturing efficiency. In this animated video, we illustrate circulating tumor cells in the blood of cancer patient being captured by magnetic wire, mag wire, within an arm vein in a single path. When present, CTC is shown here in green, often constitute only a tiny fraction, about 1 in billions of the cells in blood. To capture these cells continuously from flowing blood, the magnetic wire, mag wire, is inserted into an arm vein through a catheter, and magnetic particle coated with an anti-ABCAM antibody are then infused short distance upstream of the mag wire. CTCs are rapidly labeled by the magnetic nanoparticle as the cell passes through the magnetic particle infusion zone. The labeled CTC and free magnetic particles are captured just downstream by the magnetic wire, while unlabeled cells flow fast without bonding. So let me tell you my research summary and introduce those who helped the project. So my research work are primarily focused on the developing smart healthcare devices and smart healthcare materials. As part of fulfilling precision health in the real world, I have developed and tested a functional prototype of the precision health toilet system that could contribute to a continuous health monitoring that can generate meaningful digital biomarkers. Other works that I have focused on are developing blood-based diagnostic system utilizing iron oxide nanoparticle and catheter-like implantable devices. I also hope that my entire work can be useful in global health applications, since I always aim to devise widely deployable, economically cheap enough, and smart healthcare materials and devices. Here is the full list of scholars and physicians who helped and supported my project. As you notice, they are from wide variety of interdisciplinary fields of study. I sincerely thank them for their support and help, and thank you very much for your attention today. I hope I convey my enthusiasm in precision health to you. Thank you so much.
감사합니다. 식사 시간이 한 30분, 20분 남았던 것 같은데 재밌었습니다. 예, 그 질문해 주시기 바랍니다. 그 언뮤트 시키고 그냥 말씀해 주시면 돼요. 제가 먼저 좀 시작을 하면 이게 그 아까 그러니까 사실 그 양변기가 굉장히 싸더라고요. 그러니까
네, 그렇습니다.
얼마 전에 한번 집에 있는 화장실을 수리를 했는데, 근데 이게 이런 식으로 스마트 토일렛이 됐을 때
예.
얼마나 올라가죠?
예, 저기 교수님, 저희가 지금 카나리아라는 회사를 지금
예.
만들었고요. 그 카나리아라는 회사를 통해서 저희가 이제 첫 번째 스마트 토일렛을 프로토타이핑을 하고 있는데요. 거기 정말 감사하게도 그 저희가 원래 일렉트로닉 비데를 사서 저희가 다 안에 있는 부품을 뜯어서 저기가 이제 그 시스템 위에 저희 시스템을 얹힌 건데요.
아, 맞다. 예.
예. 그 시스템 위에서 그 시스템을 그 소유하고 계시던 사장님께서 직접 전화를 하셨습니다. 그 회사 사장님께서요. 근데 그래서 저희가 이제 그 가격 견적을 내봤더니 이게 프리미어 라인급이면은 저희가 충분히 가격 경쟁력이 있겠다 해서 약 한 지금 50만 원에서 100만 원 사이 정도의 가격대를 저희가 지금 첫 번째 디바이스를 목표로 하고 있습니다. 양변기 자체는 한 250불에서 비싼 건 한 1000불 정도. 그러니까 한 30만 원에서 한 120만 원 정도 하는 걸로 알고 있습니다.
많이 비싸. 뭐 잘 만들어서 가격을 다운시키면은 많이 되겠죠. 예. 또 다른 질문 있으신 분?
예, 점심시간 전이라 아무래도 다들
그런 것 같습니다. 여기 지금 한국 시간으로 11시 40분이거든요.
네.
그 남성 화장 변기에는 뭐 생각을 안 하시는 거죠?
남성 양변기에도 남성 그러니까 소변기 있잖아요.
소변기.
예, 소변기에도 그냥 심플하게 저희가 그런 센서 같은 거 있지 않습니까? 뭐 옵티컬 센서나 아니면은 소노 센서를 붙여서 그런 저기 유속 같은 걸 지금 재보려고 하고 있습니다. 유속하고 유량 정도.
중요한지는 잘 몰랐어요. 예.
예, 그게 결국에는 남성 중에 90%가 이제 85세에서 90세 정도 되면 이제 90%가 고생하게 된다는 그 전립선 비대증이라고 있습니다. 근데 전립선 비대증이 얼마만큼 진행되는지 알기 위해서는 결국에는 유속이 가장 중요한데요. 이제 남성용으로 그렇게 개발하고 있습니다.
I see. 예. 다들 밥을 먹으러 가려고 하는 것 같습니다. 예. 오늘 감사드리고요. 저희가 이거를 녹화를 해서 또 교수님들이 보시기 때문에
네.
잘 또 해서 질문 있으면 이메일 드리도록
예.
하겠습니다.
네, 감사합니다, 교수님.
예, 오늘 발표 감사드리고 다시 한번 제가 대표로 박수를 드리고 예, 감사합니다. 이제 식사를 하시고요. 이 오후 세션은 1시에 그리고 2시에 한 번씩 더 남았으니 많은 참여를 해주시면 감사하겠습니다. 예.